Hello, and welcome back to Learning with Lee. In today's episode, we are going to continue looking at merge sort, dynamic memory allocation, and pointers. In particular, today's episode is going to be focused on this merge function that I've created in order to do the final step of the merge sort algorithm. And just as a reminder from last time, the merge sort algorithm is when we take some array of values, split them up, then, once they're down to having a single value and are effectively sorted, we merge two of them together in order to get a sorted pair. And we do this all the way across. Then we move down a level and create sorted quadruplets. And we have these set of them. And we continue to do that until we recreate our full array except having it sorted. And its advantages are that it's really elegant, it's fairly efficient, and it happens to be overall a very good sorting algorithm. So, what we're taking a look at here now is this merger. And as we've already seen, we're taking in an array as an argument, and any changes that we make to that array, because it's passed in by reference, reflect in the original array. So it's not like this is affecting a copy, whereas these ones here, because they happen to be passed in by value, are effectively copied. So the first thing we need to take a look at for what we're doing with this merge is this here, which is the number of elements. And that's because right now we have our start index minus our end index. So let's just pop over here. And for simplicity's sake, let's take a look at this one here, which I believe has 10 elements in. So in this case here, to understand why this does what it does, what we're looking at here is that if I have this one here, which is my 9th element, and this is my 0th element, I have 9 minus 0 gives us 9. However, we actually have 10 elements here, so I need to add in 1. So that's why over here, if this will pull up, you'll see that I have this 1 added in to this subtraction, and that's to convert it from that 0 base to effectively 1 base. Then the next thing you're going to see here is I'm creating what's known as a size t. And you can see here how it pops up saying that's in 64-bit unsigned int. And what this happens to be used for is basically this function here, Sizeof, gives you the number of bytes that an integer uses. And this one here is our number of elements. And what you'll see is that Sizeof is actually 4. And this matters for what we're about to do down here, this call to malloc. And malloc basically is a version of alloc or allocate. And there's a few different versions. There's malloc, there's alloc, and there's calloc. Calloc is similar to malloc, except rather than just having a single element, what I also give it is the number of elements. So I would give it something such as num elements and size of an integer. And this would end up producing the same effect as doing this here. The major reason why I chose to go with doing this up here, as well as then also using malloc, is that I actually need element size down lower. So it's a bit cleaner just to do that math once and use malloc. Though, in general, if you don't need to reuse this in the future, calloc is a bit of a cleaner way to do this. And what malloc produces, it's what's known as a void pointer. And you might have noticed void on some of these functions up here. And all that void says is that it doesn't return anything. And a void pointer is something that could be a pointer to any type. It's saying that the system doesn't know what type you're pointing to. It just is saying, here's this block of memory, use it as you wish. And what I have to do then is cast it to an int pointer so as that I can then use it to basically act as a temporary array. And one of the important things here is that I can't just create another array in here. In case I were to go, say, int, and I'll just call it tr, do this, and go, okay, I know how large array is, so I can just use like num elements. And you might remember from our discussion on arrays a couple episodes ago why you can't do this, because this isn't a constant variable. And that sort of would be a bit of a oxymoron saying that something is both variable and constant, but it's a matter of it is not constant, and as such, it's not going to be able to create this array correctly. So what we have to do is we have to dynamically create it, and that means dynamically allocating memory. And that is where the calls to alloc, malloc, and calloc come in. So we end up doing this, and it creates a pointer. And a pointer acts very similar to how arrays are done. And an array is basically just done using a pointer. I sort of demonstrated this earlier in case we go back and treat this similar to my mailbox example of earlier. And I know where this one is, and it's, once again, a block in memory. Then what I can do is I can just go, let's add 1 to it, or do something like array sub 1, or array sub 2. And that's one of the reasons why we start at 0 for counting when it comes to arrays. Is that what it is it's a pointer to this number here. So what you're doing when you go array sub some number is you're basically adding some value to that. And what it's doing behind the scenes then is that it's going, okay, I'm going to convert this memory location into some unsigned integer. And I'll just call that I for now, and for simplicity's sake, and make this a bit larger. But we got that, and then what we're doing is we're adding in whatever number you add to it. So if I go, let's say I sub 3. So basically, I sub 3 is equal to, in this case here, I plus, and it's, plus 3 times the size of whatever type you have in there. So if it's integers, in my case here, it would be 4 bytes. In case it was characters, it would probably be 1 byte. And it does this behind the scenes for you. So if I do, in this case here, just something like temp array plus 1, and I'll be doing some stuff, as well as you can see with pointers down here, I'm using it the same way as I would an array, just to make this a bit clearer for how this section is going and what I'm actually doing with it, in terms of copying from one array into the temporary array. And basically, an array is a pointer. There are some differences that we can get into in the future when we start dealing with arrays of pointers, because those happen to be different, as well as treating how pointers to pointers work. And you've already seen some of how this works when I did the earlier example of something by passing something by reference by adding the ampersand in front of it as an argument. And what that's really doing is that when you end up, in case, say, I call merge up here, and I pass in this start index, and it's taking this here, it's effectively giving it a pointer to that location, and that's treating it as though it were the same. A bit more of the classical way you'd see this done in C rather than in C++ would be that down here, what I would do is I would say, okay, I have an unsigned int pointer, and up here, what I would have to do is rather than passing in this value itself, I'd have to pass in its address. And the way you get the address of some variable is with this ampersand. And this basically just says then that start index is the name of some spot in memory. I want the integer that represents that spot in memory, basically similar to if you have some P.O. box number. It's like send this to Mike Smith at blah 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 for their address. What you're saying here is that in case we're smart enough to know just off of who Mike Smith was, which basically is what the start index is, this is basically saying give me that address. And address is the technical term for what this actually is, rather than saying something like P.O. box or any of this other stuff I've been using. But you can see how those two are related, similar to somebody lives at some address, and it's the same reason in memory for that. Then, down here though, what we're going to do with this is we're going to copy the sorted elements from our main array into this temporary array. And the reason why we can't just reuse this main array is that then we would wind up writing over some of the existing memory in there. And we would end up basically with duplicate information, because unless it was already sorted, as soon as we would go to, say, in case we were trying to reuse the same array, and let's say we're using 3 and 5 here, okay, 2 would come over, 3 would end up overwriting 8, and we would wind up with 2 3s, whereas previously we had 2 8 3 5, it would be 2 3 3 5, because of the way that would work if we tried to use just a single array for it. So what we end up having to do is we have to use a second array to copy between the two of them. And I'm going to flat out say that this is deliberately not as efficient as it could be, in terms of how it's using this, so as I can show you two different ways in which you can do this. The first is us creating this temporary array in here, and us passing it through here, and probably for homework, the homework assignment for this one here, what I'll have you do is modify this so as that what you can do is you can end up having it so as that it passes in a secondary array, and basically at each layer of the merge, it swaps the two arrays so as that you can end up doing it correctly in terms of going, okay, I'm going to use one for sorting and just copy them back and forth. And I'll show you how that's done probably in the next episode, but for now let's focus on this. What we have down here then is one of the major things to understand about all these allocation things is that there's two different types of memory in your computer. There happens to be the stuff that you're creating whenever you go, okay, I'm going to create an unsigned int here, whenever you're creating size t's, or whenever you were creating this original array back in intro of some size here. And all those go on what's known as the stack. And it's fairly quick in order to create that memory because it's a matter of you know how much you need on the stack at compile time. At runtime, though, what you then do is you use the heap to dynamically allocate memory. And it's a bit slower, and that's one of the reasons why what I said that this is deliberately not as efficient as it could be, because one of the things that we're going to take a look at is the fact that this does many calls to malloc, because it ends up doing a merge at every single one of these recursive calls, and as such, it ends up being much less efficient than it could be if we did only a single call to malloc. But as I said, that's something we'll probably examine in the next episode, when we take a look at changing it so as that it ends up using only a single malloc call rather than these multiple malloc calls on every single merge. So one of the problems, though, is that with the heap, you might not always have enough memory available to you to create the amount of memory you need. So in this case here, if I tried to create some massive amount of malloc, such as just start adding on zeros here and create a massive amount of memory that I need, I might not be able to get that because either the operating system isn't willing to let me allocate that much memory, or the rest of my program takes up so much memory I don't have much left to use, etc. And in case there's a problem like that, it's going to return what's known as a null pointer. And in general, it does expand to 0, but you can't guarantee upon that because that can vary based upon your hardware. And in general, anymore it's 0, but it's better to just use the macro null. And you'll see this a lot when we get into other languages. In C and C++, it's the capital null. When we get to other languages, it'll just be lowercase null. But that has to deal with some differences in design philosophy as well as also the general coding patterns and standards that people use. It's that constants in C and C++ always end up being full capitals because that's how it's been for a long, long time since really Kernighan and Ritchie wrote the C programming language. Then down in here, what we have is a loop, and this is what we're going to be doing in order to do the sort in terms of saying, okay, we have something, because right now what we have is we have these two arrays. And the way in which I'm doing it is I'm using effectively this one here with two different indices in order to represent two subarrays within that parent array. So within here, I might have one that goes from 0 to, in this case here, 2, and then the next one might go from 3 on over, 5, not 6. And as you can see, even experienced people get confused with the 1 base versus 0 base sometimes, but you might have these two arrays. So what we have over here is we have our start index, which in this case here would be 0, our split index, which for me, I could use technically either one of these, but I'm using 3 for this one here. So the start of the second set of these. And then we have our end index, which would be 5. And so we can effectively, just using these indices, have multiple arrays without having to have dynamically allocated subarrays that we create and then merge those together. So it manages to save us a little bit on memory, a little bit on mallocs that we end up using during this. So what we then do is that we have these three ones here. And these are just going to be things that allow us to iterate over, as in start here, go to this one, go to this one, start here, go to this one, go to this one. And the three of them happen to be used in order to cover, in the case of I, it happens to be used to go over our temporary array. A is our one that starts at the split index and ends at the index directly, starts at the start index and ends directly before the split index. And B happens to start at the split index and end at the end index. And the way in which we do that down here is that what we're going to do, first off, is as we move through this list, we need to increment I so as that whatever happens to be, basically when we do our first, whatever is first from A or B, we insert it into the first position in our temporary array. Then we need to go to the second position in our temporary array and insert whatever is next. So that's the whole I is 0. We are guaranteed to have an equal number of elements as our end index minus our start index plus 1, as you can see over there from the 9 minus 0 plus 1 that I showed. So we need to go until we end up dealing with all of our elements in here, because in case we end up with effectively a fewer number, we're going to shrink our array each time and wind up with an incorrect result. Or we're going to grow our index each time and also wind up with an incorrect result. So it needs to go for the number of elements. And once again, it's less than the number of elements because we're starting it at 0 base. And as you can see, increment there just to go through that. So then down here, this is a bit of a interesting spot here to make certain that everything is correct. The first thing that we're checking is that in case we've already been through every element in the first array, so within A, because A is starting at the start index. So in case it happens to have reached the split index or somehow by some glitch has gone beyond the split index, we only want to take elements from B and put them into the temporary array. We don't want to take any elements from A because at that point there, as soon as we start taking elements from A, we're actually taking stuff off of the front of B. Then what we want to do, though, once we've made certain that that is taken care of as a possibility, we also want to then check if B is less than A. In other words, right now, because of the fact we're doing a minimum sort, so the minimum element goes at the beginning, if B is less than A, we want to insert it, but only if B is less than the end index. So in the example I showed over here, in case B happens to be over here, pointing at this one here, and it's past this end index here, we don't want to compare 8 with any of the values in here because we might get a wrong sorting at that point, and it could give us incorrect values, such as in case this one here, rather than 8 were 1, then it would end up basically erasing this 8 here. We would then skip to 9, probably get this 3 here, but we would wind up with an incorrect number in there. So that's the reason why we have to make certain that B is less than the end index. It's the same reason why we have this one here, and I just have this all as part of one Boolean statement right here. So then what we do is we insert whatever one happens to be closer to it, and then so as our comparisons can work correctly, let's say that I took one from A to begin with, to go with our example from here. A starts out here, does this, we insert it. Now A has to move 1 over to 8, so as that it's the next one that we take a look at, or more accurately, what we would actually have here. Yeah, because this one here isn't sorted. Let's start out down here, really. A starts out at 2, B is over here at 3. And what we have to do then is 2 comes down, A then points over to 8. B still points to 3 because we haven't inserted 3 yet in here. We're then going to insert 3. B moves from 3 over to 5. And at that point there we compare 8 and 5. 5 gets inserted, B is beyond this point, so the comparison doesn't even matter. We just insert A down into here. So that's the whole reason for why we're incrementing only one of these two when we headed through here. If we incremented both of them, we would wind up with basically A would get inserted, we would skip both A and B over, and 3 would get lost from our array forever. As well as then we would wind up with a weird situation of us not being able to really insert A or B, because we would wind up with some really weird glitchy stuff because of the way this loop is set up. But that ends up populating our temp array. And once we are done with that, what we need to do then is copy the information in that array back into our original array. So what we're taking a look at here is, you remember how I said you can basically add an element to something to represent doing this whole sub thing. So basically this would be the same as ARR plus A. Well, in order to show this, because of the fact that we're dealing with pointers here, and there is a problem with that, because this actually gives us the value at that location. And what this gives us here, by doing this addition, it gives us a pointer to that location. And memcopy cares about pointers. I could also do this, just to sort of show off another way of doing it, by doing this, but then I would have to get the address of the array of that start index. And that would be the only way that this would work. Because this one here is actually giving me that value. It's not giving me a pointer to that value. It's giving me that value itself. So it's one of the main reasons why there are certain times you want to use the subscript notation here, and certain times you want to use more or less the addition notation, and it can make it a bit cleaner for whether or not you want pointer, like in this case, or you want to affect the actual values that are being pointed to. So what memory copy does is it says, I take this second element, I take a certain amount of memory equal to some size up here. And it's important to remember that you need to include the size of whatever you're doing. So when it's something like the size of an int, you care about the actual size of an int, because otherwise it's just going to give you num element bytes, which will give you incorrect values for what you're copying over. So what you need to do then is you need to copy this amount of memory from this location, well, starting at that location, going to this location referred to by this pointer. And then lastly, we have this free call. And free is something that any time in which you're going to use malloc to create memory, you need to let the system know that you're done with it. Because created memory by malloc, alloc, calloc doesn't follow the usual rules of scope the way that something like num elements does, where as soon as I leave these braces down at the bottom here, it's going to be deleted automatically for me. Anything I create with malloc, alloc, and calloc that's on the heap, though, that's going to stay there. And it's going to take up space. And whenever you end up having a situation where you end up creating memory on the heap, and you don't delete that memory later on via free, you have what's known as a memory leak. And these are very common problems even in massive industrial software, things that have lots of professionals looking at them who've been doing software for a long time. Memory leaks still occur. And they are really, really hard to track down and deal with, but they are very important to deal with. And the way in which you solve it is that anytime you're going to malloc something, you need to make certain that you clear it at some point later with free. It doesn't necessarily need to be within the same scope, because in case, for example, I was returning, and we're going to get into how we would actually return a different array in case we wanted to make a copy of the array, and return that copy without modifying the original array, we would have to basically malloc something in one of these scopes, and then at a later scope, free that memory that we had allocated. So I think that's enough for today's episode. What I would recommend doing is spend some time looking through here. If you really want to get a jump start on what we're going to be discussing in the next episode and see if you can figure it out for yourself, figure out a way in order to move this malloc call so as that we only do it once. Probably, I'll even give you this hint, it should happen in this call to merge sort, and then be passed in to merge sort recursive. And I'll get into how that will be done next time. Thank you very much for watching. I hope you have a wonderful day.